So we're going to be talking about transformer-based language models, and for this to make sense, you kind of need to have seen Monday's lecture or have been familiar with the transformer already. I'll kind of do a very quick review. But if for some reason you weren't able to make Monday's lecture and you haven't had a chance to catch up, you might want to go see that now and watch this later, because this will make a lot more sense if you've seen Monday's lecture. Okay, so today we're going to be talking about transformer-based language models. And as you can kind of see here, there's a lot of them. So in short, they've like completely transformed, no pun intended, NLP. And if you're doing kind of NLP stuff, you're probably going to use, embeddings or, actually fine tune one of these models. And so I want to give you guys a sense for this landscape, what the different models are intended for, kind of their strengths and their drawbacks. And so that when you go to use a language model to create representations for whatever downstream NLP task that you need to do, that you'll have a sense for how to navigate this kind of somewhat large and somewhat disorganized and quickly evolving landscape. And so if you think back to a lecture we had a couple of weeks ago where we talked about word embeddings with a model like word2vec or glove, you'll recall that like one of the features of that was that a given word will always have the same embedding regardless of its context. So like, river bank and like robbed a bank would have, the word bank would have the same embedding. And actually it's like pretty common in English and in many languages that a single word will have quite a few meanings. And this is particularly common with commonly used words. And so it can be a big issue. It's also more common with words that have been around for longer. And we saw that this was kind of one of the drawbacks of glove or word2vec style static word embeddings. And so I'm going to start by saying a word about contextualized word embeddings. And actually a transformer-based model is not required to contextualize word embeddings, although we'll see that these kind of the transformer-based models came to dominate for reasons that we talked about, last class and that are going to come back up again today. But I'm going to start with a contextualized word embedding model that's actually not transformer-based, and that is ELMO. And so I think ELMO is from 2017. And was a prominent model in the development of contextualized word embeddings that came kind of a little bit before people started using the transformer as a language model. So the objective in ELMO, like in kind of other traditional language models, is to predict the next word in a sequence. And ELMO helped to popularize, what's been a very kind of dominant approach, which is that you use a pre-trained language model to create representations that you then use on different downstream tasks. So you don't care about predicting the next word in a sequence, but the representations that you can get from a language model, which can be trained on just massive amounts of unlabeled data, can then in turn be used directly or fine-tuned with a small labeled data set to whatever downstream task that you actually care about. And so ELMO is based on an LSTM, which you guys have all seen. And so you feed in word embeddings and they get passed into this LSTM, and each embedding is combined with the history to make a new representation. And there's two layers of that. And so that's giving, contextual representations for these words because those red representations depend not just on the input, but also on the history. And I think the kind of idea behind the name, and we'll see that it kind of kicked off a Sesame Street language model theme, is that there's like a Sesame Street segment where ELMO asks someone to define what a word means. And, they'll sometimes say, well, it depends, use it in a sentence, right? Which goes to, again, to show that kind of context matters. And like Sesame Street is ultimately a show about, teaching kids language. And that comes up as like, an important Sesame Street theme. Okay. And so if we just did this forward, you know that that could be an issue because what a word means depends not just on the previous words in the sequence, but also on the subsequent words. And so ELMO is a bidirectional LSTM, you know, just like we saw that OCR uses a bidirectional LSTM. And so there's a forward model, and then separately, you run a backward model, where in the backward model, you just pass it the sequence backwards. And besides that, it's the same as the forward model, but it's being trained on these backwards sequences. And then you need some way to put this together because you don't want a forward and a backwards, you know, embedding. You want a single embedding for each word in the context of the training data. And so ELMO creates contextualized embeddings by concatenating the hidden states and the initial embeddings across the forward and backward LSTMs. And then it just takes a weighted sum of the hidden states and the initial embedding vectors. Oops. So you see that here. And so there's these, you know, there's the two layers of hidden states and there's the initial input. Those are all, you know, there's the initial kind of lookup for the word, you know, which is going to be kind of the static embedding that you look up, but that itself is a trained parameter. And then you have these contextual representations. You concatenate the forward and backwards ones, and then you multiply across the three layers of the network using a weighted sum where those weights themselves are parameters that you learn. There's also other details to this, like, and so to create those initial embeddings, it's a little bit different than what we've seen so far, where you just take a word and you look it up in a lookup table to get the embedding. And so ELMO will use something called like character level embeddings, and it's kind of involved. And so we're not going to talk about that, but just note that there's like other things that are kind of different about this, like how it embeds the words to start with to get those green vectors. Okay. Anybody have a question about ELMO? Nope. Okay, so now I want to move into talking about this kind of landscape of language models that use the transformer, which have come to kind of completely dominate this space over the past few years. And so the first example of a standalone transformer-based language model, to my knowledge, was the OpenAI GPT. And so if you guys kind of follow this literature, or just follow news about it, you've probably heard of GPT-2 or GPT-3, which I'll get to a bit later. But right now I'm talking about like the original GPT. Like there was a original GTP that people, you know, you wouldn't use this nowadays, but anyways, and so the original transformer, like we saw on Monday, contained a language model that was the decoder side of the transformer. Because if you remember, the objective of the decoder side is to predict what word comes next. And that's kind of what a traditional language model is. How does it do this? Well, it masks future tokens. So this decoder model doesn't have to be coupled to an encoder model, as we saw it was for the original transformer for doing machine translation. You can just take the decoder model by itself and use that as a standalone language model, which is what the OpenAI GPT did. And so I just want to kind of quickly review a couple of concepts from last class in the context of what an encoder transformer and a decoder transformer does, because that's going to be relevant to kind of how these different language models differ. And so in encoder self-attention blocks, a position can see tokens from both the left and the right. Whereas this is not the case for the decoder blocks in the transformer. And the idea here is akin to predicting the next word given the previous context. Obviously, if you could see all the words, you can trivially like predict what they are, right? So that wouldn't be a very interesting model. So let's just have a quick recap of self-attention without masking first, which is what the encoder of the transformer does. So for each input token, we create a query vector, a key vector, and a value vector by multiplying by the weight matrices, the query matrices, the key matrices, and the value matrices. You know, these are all learned parameters. And so we create those vectors. They're going to be lower dimensionality than the inputs, which are just kind of looked up in a lookup table. And then we take the dot product between the current query vector and all the key vectors in the sequence. And so in language models, that sequence is going to be something like 512 words long. And so you're going to take the dot product between the query vector for the current word that you're considering and all the key vectors to get a score of how well that they match. And then you're going to take that and you're going to softmax it and multiply it by these value vectors that you computed. And then you're going to add those up to create the attention vector. Okay. Okay. And so that gives you these vector outputs, and then you'll concatenate those. There's actually, remember that attention is multi-headed, and so you do this something like 8 times, and then you concatenate and multiply them to get a vector that's the right dimensionality to feed onto your next layer. And so that is attention without masking. And so when we do attention with masking, steps 1, 3, and 4 are the same. What's different is step 2. And so you're still going to compute these query, key, and value matrices the same. You're still going to, do these, all of these dot products. But what's different is when you get to step 3. And so essentially what you do is any token that is ahead in the sequence that you can't see, before you get to the softmax, you set its that dot product, you change it from whatever it is to negative infinity, and then you take the softmax, and that means that you've essentially ended up putting 0 attention on anything further along in the sequence, which is equivalent to not being able to see it. And so that effectively, you still, just like with the encoder side, you still have this advantage of the transformer in that you're not feeding in like tokens one by one. You feed in all like 512 tokens at the same time. You do your attention calculations where you can attend to everything just like you would with the encoder. But then on the decoder, before you softmax those attention scores to get the attention kind of weights, you just set the ones from further along in the sequence, a negative infinity, which when you softmax that, or a very large negative number, when you softmax that, that gives you an attention score of 0. And so now, you're only paying attention to those previous tokens. And so, this is just showing it here kind of in a visually intuitive way where you have a sentence with 4 words. And you create the attention scores, but then you're gonna mask the ones think of it as kind of like a triangle, and like the top right of that triangle is words that come later on in the sentence that you can't see. And so this matrix, like half of this matrix is gonna be zeros, and you're only paying attention to the part like below the diagonal of the matrix, which is the parts that you've already seen. And so then that's your attention scores. And so that's how the decoder works. And so that's what GPT is going to do. The original GPT, that's going to take those decoders, decoder blocks, just like we saw in the transformer, and it's going to stack 12 of them. But because there is no encoder, it no longer needs the encoder-decoder attention layers that we saw last class. And then the training objective is just to predict the next word. Okay, so this is kind of a visual of that. You're going to take your sequence. And again, unlike in the LSTM that we saw with ELMO, with the transformer, you feed the whole sequence into the model in parallel, and then you're going to be able to kind of attend flexibly to the sequence. But since we're using masked attention, you only allow to attend to things that come previously. And you stack up 12 of these decoder blocks, and then you have a fully connected layer and a softmax that goes to every word in the English vocabulary, and that allows you to predict what word came next. And that is GPT. Okay. So one of the things that GPT emphasized is that you can transform the inputs of the model to configure the model to perform different downstream tasks. And so if you want to do a classification and your inputs, you add these special like start and extract tokens, and that tells the model to have this kind of fully connected layer at the end that goes to like a class score. If you want to do entailment, where you're saying whether like a premise is equivalent to the hypothesis, again, you add certain tokens and that tells the model to do that. If you want to compare, like say compare two sentences or two sequences for their similarity, again, if you input kind of the model in the format that's shown on the left, the model will know that that's what you want kind of at the end of it. Multiple choice questions, these are just the examples they give in the paper, right? So by feeding the inputs into the model in a certain way with certain arrangement of tokens, and you tell the model what task you want to perform. Sorry. Okay. So at first, it kind of makes sense that the OpenAI transformer used the decoder blocks to make the model because the decoder is a language model. But if you just use the decoder blocks, the problem is that, like, in contrast to ELMO, the OpenAI transformer is not bidirectional. So in theory, I guess you could feed the sequence in backwards, but then you would need a way to combine the representations like we saw with ELMO. And so in contrast to the decoder blocks, the encoder blocks are not a language model. They're creating these representations, but they're not, they're creating representations. They're not trying to kind of predict what word comes next, like a language model. And to create representations for each word, the encoder attends to all other positions in the sequence that was fed into the model. We'll now see an influential paper whose innovation was to realize that encoder blocks can be used to create a bidirectional language model through masking. Okay, and so that model is Google's BERT. BERT stands for, it continues the Sesame Street theme. It stands for Bidirectional Encoder Representations for Transformers. Which is a descriptive name. It's bidirectional in that it considers context from both directions, like with ELMO and the bidirectional LSTM. Encoder refers to the fact that it stacks the encoder blocks from the transformer. And you see representations, well, sort of its most remarkable feature is creating representations that can be used for a very diverse set of downstream tasks. And so this marked kind of a major leap forward in NLP, developing a transformer-based language model that it worked a lot better than the kind of like naive application in the original GPT, because it had these bidirectional contexts. So the transformer encoder reads the sequence all at once. So that makes it bidirectional, or in some sense non-directional, right? Like it just sees the entire sequence, which in BERT is going to be up to 512 tokens, which are like basically words. And BERT trains the encoder as a language model by using an approach that it calls masked language modeling. So it takes 15% of the tokens, these kind of subword tokens that are mostly words, but if you have certain endings like ing on the end of a word, that will be its own token. And of those 15% of randomly sampled tokens, 80% are replaced with the mask token. 10% are replaced with a random word, and 10% are kept the same. And the model is trained with a loss that compares the predictions for what word is at that step with these tokens. And so if it sees a mask, it has to predict something based on the context, but it's also sometimes just seeing a random word or the correct word, which just allows the model to kind of to be more robust. It can do a good job of predicting tokens that aren't masked too, because sometimes the masked tokens are the actual word. And so in the training objective, it benefits from having a good representation from words that aren't masked, and also from being able to recognize that sometimes words are just wrong. Okay, and it's kind of a bit arbitrary why 15%, like it doesn't say. I mean, it just chose that. It worked. So this is an illustration of masking. And so there's a sentence you pass in. I'm going to tell you about this class token and what that is for in a minute, but ignoring that for a second, look, you see the green words, you pass them in, but you're masking out some of them, and you're going to pass in a 512, up to 512 token set of text. You're masking out 15% of those. It goes into the this multi-layer transformer where you're stacking up these encoder blocks from the transformer. And then at the end of that, you have a fully connected layer and a softmax that goes to all words in the vocabulary. You use the output of those 15% of words that you've either masked or kind of kept the same or replaced at random to evaluate how the model is doing. Okay, so a second key part of the training objective is next sentence prediction. The model receives pairs of sentences as inputs and predicts whether the second sentence comes directly after the first in the original corpus. And so in training, half the time, in training, essentially, like you're feeding in like pairs of sentences, and half the time they're consecutive sentences, and half the time they're just randomly kind of chosen from the corpus. And the other kind of, it's a multitask objective. And in addition to predicting the mask tokens, the model is also just predicting a classification of 0, 1. Does the second sentence come after the first sentence or not? And that's a 50-50. And so it's kind of, again, like trying to, make the model take into account kind of the broader context in a coherent way. And some people argue that, and there's some evidence that this isn't actually important, but it's there. And so the way it does this is to insert a special class token at the beginning of the first sentence. And then there's a separator between the first and second sentence. And then you're feeding in like, and so you have that's how you feed in information kind of in the training. So you have kind of a first sequence and then a separator token in a second sequence. The class token at the top there as the output, it's going into the next sentence prediction model instead of into a masked language prediction. And so for that class token, the output, instead of the output being a probability for every word in the English language, it's just 2 probabilities for is next or not next. Okay. So this is how tokens are input at training. And so you put in like the class token and the separator token, and then you have 3 embeddings. You have to embed the tokens, you know, you're kind of looking those up in like a word embedding table that itself is kind of, you know, those are parameters of the model. And then there's also these sentence level embeddings for the 2 segments that you create. And finally, there's the positional embeddings, just like we saw last lecture. You need these positional embeddings to tell the transformer the order of this sequence since it's all being fed in at the same time. Okay. And so this is the training architecture. You're passing in mask sentence A and mask sentence B, and then you have the class token, and your objective is the next sentence prediction and the masked language model, where you're trying to predict the mask tokens and whether the sentences should be paired. And then you can adapt this to various fine tuning tasks. And so just to give some examples from the paper, a sentence pair classification. And so you see a bunch of acronyms there, which are just, this is like a common task in NLP benchmarks. And these are different benchmark data sets. You know, so do these sentences kind of belong together? I mean, obviously it should do well on that since that's how it's trained. Single sentence classification tasks, like if you want to classify this as kind of positive or negative, you can fine tune that in the context of this model, you know, just by having your labeled data. And then when you feed it into the model, you just kind of essentially use the same structure that it was pre-trained on, but now what you're feeding into the model is just a class token followed by a sentence, and then you're training that classifier that is output from the class token on your labeled data. There's also question answering tasks. And so what you do with question answering is you're giving the model like a question and a sequence of text, like where the answer could be. So then, you know, the way you feed it in is to have, again, like kind of a class token that's telling it what kind of task it is, and then a question, a separator, and a paragraph where you're looking for the answer. And then the output of that is the start and end span for the paragraph. So think about like, you know, asking Google a question. And when you click on the website, it will highlight the answer. Or like if you have like a Google Home device or whatever, you can ask it a question, it will read off the answer from, you know, somewhere on the internet. And that's, I mean, that's what it's doing. I mean, BERT underlies Google search. And when they put BERT into Google search, it was like the greatest improvement in search, kind of in search history. And so you can like, that's kind of what it's doing. You know, sort of, although there's a retrieval component there too, right? But essentially there's a model, you can fine tune BERT to do this question answering and again, you know, like with any downstream task in language modeling, we are using unlabeled data. It's an unsupervised task because we trivially know what the mask tokens are because we mask them. Whereas to train kind of a question and answer model, you're using kind of exactly the architecture of BERT, but now you're feeding it labeled data that tells when to start and end the answer. And the squad data set is the benchmark for question answering. And then there's tagging, you know, things like parts of speech tagging or named entity recognition, and you can also use it for that. And so it's just really flexible in the sense that, say, like, you know, Google pre-trained the model to provide these embeddings, and then you're taking their pre-trained model, but you're doing further fine-tuning that allows those weights to change. And in order to fine-tune it, all you have to do is kind of feed it the right input, let the model know that you're doing single sentence classification or you're doing question answering, and then you need to have your labeled data that you're using to fine-tune that model. But this is essentially like I mean, this is what kind of ELMO advocated, and this is like kind of the paradigm for how NLP works, that you can take this model that was pre-trained on a massive amount of text and then take your much smaller labeled data set and fine tune it. And the way that the architecture is built kind of allows you to fine tune it end to end just through these kind of class tokens and through, you know, putting the labeled data, you know, depending on what you're doing, if it's a classification task, right? Like then that output is just like a number, right? Like 0 or 1. This is like left leaning or right leaning. And so that comes out of the class token. But something like question answering is what's called like a text to text problem. And so you're feeding it in a sequence of text, the question and the answer, or sorry, the question and the paragraph. And the output is the portion of the paragraph that answers that question. Or something like part of speech tagging is a label on each of the texts that you feed in. And so then you're not doing anything to train or to fine tune on the class token, but you have labeled data for each input to the sequence. And so you can see how this is just kind of a really powerful approach in context where, you know, by and large, if you have to have human created labels, the labeled data sets are just tiny, tiny, tiny compared to what the model, like the language part of the model was pre-trained on, but it contains all that information from the unsupervised pre-training. Then you can further fine tune it on your specific task. And so this is like a paradigm that you are very likely to use if you do any kind of NLP work. Okay, so that's one approach, is that you take BERT and you fine tune it to whatever your task is. But there's an alternative to that, which, like, say that you've already kind of built your own model, or just, you know, whatever you want to do, it doesn't really kind of fit well within BERT. You can just take the pre-trained BERT embeddings and feed them into your own existing downstream model. And the paper shows with an example from named entity recognition that this works almost as well as fine tuning. So obviously your mileage may vary depending on what you want to do, but rather than taking kind of the whole model and fine tuning it to your task, you could also you could take the representations from that model and feed them into your own downstream model. And so if you're going to do that, there's a question of which layer of representations you're going to use, because BERT is 12 layers deep. And at each of those hidden layers, you're creating a representation of that word that's been fed in. And so if you're not going to, you know, fine tune the whole thing end to end, if you want to take the representations and then use them in a separate model, you have to decide which of those representations are you going to take. And it kind of talks about this in the paper, like for a very specific task, which I think is a named entity recognition task benchmark. And so it takes different parts. And so just as a reference, if you fine tune the model end to end for named entity recognition, you get a score of 96.4. Whereas if you take the embeddings and put them into kind of a separate model that is used and you use those embeddings in a separate model that you're training for named entity recognition, the scores are, if you use the first layer of representations, it's a score of 91, which is a fair bit lower. The last hidden layer, you do a lot better. They sum all 12 layers, that's even a little bit better. Second to the last layer does pretty good. You can sum the last 4 hidden ones, concatenate the last 4 hidden ones. And so obviously there's a lot of options here. And one of the advantages of just fine tuning is that then you kind of don't worry about that. You're just doing things end to end and sort of that will give you the results. But if you want to plug these into some other kind of model that you have, and you don't want to fine tune the whole thing, you're going to have to make this decision, and which layer to use kind of likely depends on the task. And so there's a general consensus that upper layers are going to be more task specific to how kind of the model was trained. So in the case of like a pre-trained BERT, right, the upper layers are going to tell you more about like, do these two sentences, are they consecutive or not, because you've trained it to do that. There's also a paper called How Contextual Are Contextualized Word Representations that looks at BERT, ELMO, and GPT-2 embeddings. And it finds that if you take representations of the same word in different contexts, they are less similar in the upper layers, which suggests that the upper layers produce more context-specific representations, which is like sort of intuitive, because you have more and more opportunities to attend to different parts of the sequence as the representations get passed up through the model. So just to summarize BERT, which is a figure from the paper, it kind of takes the transformer-based architecture and makes it bidirectional. So it looks kind of like ELMO, but it's a transformer, not an LSTM, which means it's going to be possible to run it on, train it on way more data, because you're able to feed everything in parallel, and it can attend to kind of other parts of the sequence in much more flexible ways, and that's going to, allow it to have much better performance. One final note is there's two options you'll see. BERT base has 110 million parameters, and BERT large has 340 million parameters. Larger model is going to perform better, but that has more computational requirements. And we're going to kind of come back to this issue as we move on through the lecture, of this kind of trade-off between the size of the model and can you possibly compute it, even ignore training just for inference. Okay, are there any questions at all about BERT? Okay, so now I'm going to talk about another model called ROBERTa, which is robust BERT. And so it is produced by Facebook AI Research, and the model architecture is the same as BERT. And what's different is that it trains on way more data for longer with a larger batch size. And that's going to be a theme in this literature of how you achieve state-of-the-art performance, training on more data. In this case, like, the model architecture is actually the same. Another thing that's different, it has a different training objective. So it gets rid of the next sentence prediction. It just predicts the mass tokens. And this is another theme that kind of, when you have different language models, they'll differ in their architectures and their training objectives and in their training data. And so in the case of ROBERTa, it's the same architecture as BERT, but we'll see it's trained on different data, and they just got rid of the next sentence prediction part of it. Okay, so BERT was trained on 16 gigabytes of data, which is like essentially the Google Books corpus and Wikipedia. And ROBERTa adds another 144 gigabytes of data. So it's like essentially training on an order of magnitude more data. And that comes from a Common Crawl News data set, which is 63 million articles at 76 gigabytes. A web text corpus of just stuff scraped from the internet, 38 gigabytes. Stories from Common Crawl, another data set, 31 gigabytes. In order to train the model for a long time on this much data, they trained it in only a day, but it took 1,024 GPUs, which is why you see all these language models, like, they come from researchers at like Facebook or, OpenAI, which is affiliated with Microsoft essentially, or Google. This is not something that you do at home, or even you do in the cloud, because that would cost a lot of money. So essentially it's BERT changes the training objective, not clear how important that is, but what's probably really important is it just trains for a long time on, I mean, 104 gigabytes of text data is like, you know, many billions of tokens. And this allows it, depending on the benchmark task, to have a 2 to 20% improvement over the performance of BERT. And so this is just the table from the paper. These are all different benchmark tasks. You know, maybe we'll talk about a couple of these, but there's a lot of them. There's also more than just this, just different things that people want to do downstream. And so if you go to kind of their GitHub page from Facebook AI, like BERT, you have a base and a large. One has 125 million parameters and the other has 355 million parameters. And then you have two of them that have been fine-tuned to two of these benchmark data sets that they make available for download. And so one is fine-tuned to this Winograd schema, and that is essentially a data set where it gives there's a pair of sentences and they differ in only 1 or 2 words, but they contain an ambiguity that is resolved in opposite ways in the 2 sentences, and that requires the use of like knowledge and reasoning. And so an example from their website is the city councilman refused the demonstrators a permit because they, and then the 2 sentences differed by saying feared or advocated violence. So if it's because they feared violence, they is referring to the city councilman, but because if it's they advocated violence, they is referring to the demonstrators. And this is like a really challenging benchmark. I mean, that's like a pretty hard thing for a computer to learn. So this is like kind of one of the really challenging benchmarks. And if you're doing kind of pronoun disambiguation, like with this data set, you can get the version of ROBERTa that's fine-tuned to this data set. And I have no idea if that's like relevant to your task. But anyways, it's there. It's been fine-tuned to this data set that has 433,000 of these sentence pairs. There's also like the version that's fine-tuned to this MNLI benchmark. And this is a task where you have like a premise and a hypothesis, and you have to label it like a contradiction, an entailment, or neutral. And again, you know, not clear that kind of fine-tuning on this helps for whatever you want to do, but that's what that means. Are there any questions about ROBERTa? Okay. And so we just saw with ROBERTa that you have a model that it's architecturally the same as BERT. And so it's going to have the same number of parameters. If you want to download it and use it, it's going to be the same size as BERT. But it does a bit better because it was just pre-trained by Facebook on way more data. And so, you know, you would, like, I think like almost anyone would use like ROBERTa over BERT because you're like Facebook already did that pre-training for you. And so you can download it, it's the same size, it's going to do a little better. Now you might say like, well, like I have limited compute. And I am having a hard time downloading even all those, whatever, 130 million parameters and getting ROBERTa base to work. And so there are other options. And so that are smaller and more lightweight. And one of those other options is called DistilBERT. And so this is relevant if you need a lightweight model and you're willing to sacrifice some accuracy to get that. And so DistilBERT has half the number of parameters of BERT, but retains 97% of the accuracy of BERT on benchmark tasks. And so remember, like ROBERTa is maybe like 10 to 20% better than BERT. And so there is kind of loss in accuracy, but it's a lighter weight model. It only has half as many parameters. So ROBERTa took 4 times as long to train as BERT, whereas DistilBERT trained 4 times faster. And it was trained on the same data set as BERT. So the kind of more modest amount of text. And the basic idea, like I'm not gonna go into any of the details, but the model is trained to approximate the larger network learned by BERT with a smaller network. And so you already had BERT. Let's approximate that with something smaller. Distillation is a compression technique that you use to train a small model to reproduce a large model as closely as possible. It uses this Kullback Leibler divergence, which is used in Bayesian statistics to approximate posteriors, but works in this context as well. So if you guys are interested, you can go check that out. Okay, so DistilBERT is not the only lightweight option. There's actually like a more recent lightweight option, which I think is probably even better, which is LBERT, which stands for a light BERT. LBERT shares parameters between the transformer layers. And so if you remember, when we talked about the transformer last class, it has these multiple layers. And they each, even though they have the same architecture, they each have their own parameters. And so LBERT reduces the number of parameters by 70% by making those layers share parameters as you pass through those 12 layers of BERT. In LBERT, they don't all have their own parameters. Some of those parameters are constrained to be the same, and that dramatically reduces the number of parameters. And then the other thing it does is in the input vectors, you look those up in a lookup table, right? Which is itself, full of estimated parameters. And that lookup table is for static word embeddings, right? It's passing it through the transformer that makes those word embeddings contextual. And as we saw a few slides ago, like the further up the transformer you get, the more contextual they get. But at that input, when you look up that word in the embedding table, that is a static embedding. And the intuition is, you don't need nearly as large of a representation to represent a static embedding as you do contextual embedding, right? Because there's just far fewer kind of possible static embeddings. And so it also utilizes that. It makes the input vectors 128 dimensions versus the hidden state representations, which are the contextual ones, which are 768, just as they are in like the BERT base. And so you take these two things together, and that reduces the number of parameters by 89%, which is a pretty dramatic reduction in parameters. And another thing they do that is pretty cool is you can increase the size of the hidden representations, but still share parameters. And so there's a version of LBERT called LBERT extra large that scales up the hidden representations to dimensionality 4096. That compares to 768 in BERT, or like the baseline LBERT. And even when you scale those hidden representations up to make them huge, when you force them to share parameters, it still reduces the number of parameters by 30%. So even with those kind of huge hidden representations, the number of parameters is less than in BERT. And actually, LBERT XXL outperformed BERT and other models, including ROBERTa, on like some of the benchmark tasks. And the smaller LBERT did kind of only modestly worse than BERT, but it had, essentially 90% fewer parameters. And so you can actually do better than BERT with this extra large LBERT, which has much larger representations for the hidden states, but forces those representations to be shared between layers. And if you need something that's like much lighter weight than BERT or ROBERTa, because you don't have a very powerful computer, you can use just the LBERT base. And it's not gonna be really as good, but it's still gonna be pretty decent, and it's gonna run a lot better on your machine. Okay, are there any questions about the lightweight BERTs? Okay, so now I'm gonna go in the opposite direction. So I just showed you that, hey, there's like a lightweight alternative to BERT. But as I said, we saw with ROBERTa that, they trained on way more data and for longer using the same architecture and they did better. Well, there's been a more recent model by Google called T5 that kind of takes that to an extreme, also making a much larger model. And so T5, it's the text-to-text transformer. And there's a few things about it. So it suggests every NLP model can be treated as text-to-text. So that means even tasks like classification. And so you remember with like the, with BERT, that if you did like a classification task, let's see. So these classification tasks, the output of that is like a softmax on that class token, right? Whereas something like the question answering would be a text-to-text task, where there's an input of the text and then you're taking a subset of that text paragraph that's input and that's the answer. So that's like a text-to-text. What T5 does is it just defines every task as a text-to-text, which you can do, right? Like, the output for the classifier could be yes or no as in text and not like a, like a softmax there. So that's kind of the first innovation of T5. So the model understands what task is to be performed with a task-specific prefix added to the original sentence, much like in BERT. So you can have, there's like a task-specific prefix for translating French to English. And you can use T5 to translate French to English. There's a specific prefix for doing summarization, and you can feed it in a paragraph and summarize it. And this model was state-of-the-art in more than 20 tasks. So it just kind of blew every other model out of the water in terms of performance. And on many benchmarks, it actually is doing as good as humans. And so here you see the basic idea of it. You have translate English to German and it will translate it. Then you have, you want to say, is this sentence, acceptable? Is it correct? It says not acceptable. That sentence doesn't make sense. There's another task here, summarize. So basically kind of any task can be within this architecture framed as a text-to-text task. And that's actually like an architectural convenience. It's not actually, I don't think it's what like gives the impressive performance. So what gives the impressive performance is that this is just trained on a massive amount of data and it has 11 billion parameters. So we're talking about kind of hundreds of millions, like low hundreds of millions before. This model has 11 billion parameters. It's trained on a new data set called Colossal Cleaned Crawl Corpus. And this is going back to that theme that in this literature, like if you want to achieve state of the art, you need to train a very, very, very large model on an enormous unlabeled data set and then fine tune it on small labeled data sets, what you have for all these benchmarks, and essentially, wins all the benchmark competitions. And this literature has shown that this approach is incredibly powerful. It can achieve performance that most NLP researchers like 5 years ago would not have thought of as being possible. Okay, but you might see certain problems with this. Good luck running a model with 11 billion parameters on your computer. Like no matter how great your computer is, this isn't going to run on like consumer hardware. So I think what Google has in mind with this model is that you would be able to use it on their cloud TPU service, right? But obviously there's a cost to that. But the cool thing is that like Google open sourced their code. And so I think you will see, like, it's a fairly new model. But if you think about Albert and how it just dramatically reduced the number of parameters by sharing them across layers. And there was some penalty, but not, you know, too much. You might imagine that there could be like an Albert version of T5. And so, yeah, you're not gonna run this model on your machine, but at some point you might use it in Google Cloud, or there might be a lighter weight version of it. So if we think kind of more broadly, I mean, since this is sort of like the state of the art, so essentially, as I said, it just kind of won every benchmark competition, and it essentially is getting to the level of human performance on the benchmark. But still, like if you worked with this, you would see that it would fail in kind of unhuman-like ways. So let's decide that, you know, Google decides that this is great and they're going to use a T5 powered, you know, robot customer service representative. If you have to call them because you're having some problems with their service. So they're going to spin it out, and American Airlines is going to use, you know, like a T5 powered like customer service solution, which is kind of like a central commercial goal with all of this. Like if you're talking to like a T5, you know, powered customer service representative, you're going to know that you're not talking to a human. Like, even though it's achieving like human level performance on these benchmarks, it's still, you know, like this doesn't mean language understanding as a solved problem. And it suggests that we need more challenging and realistic, you know, text benchmarks. And, you know, that ties into the fact that it's far from obvious ex ante how well even something like off the shelf like T5 would perform on some of the tasks that we want to do. And again, you're going to need kind of labeled data that takes it towards, you know, whatever you're trying to achieve. And then like the other problem is, as we saw before, there's still biases. So you're training this on a massive amount of text, and it's going to inherit whatever biases that massive amount of text had. And so, for example, like there's these schemas that show that it can correctly classify sentences in stereotypical situations, like where the male is a doctor and the female's a nurse, but not vice versa. And so that's like another kind of issue that this has. It may or may not be kind of relevant for what you want to do, depending on what you're doing. But that is worth keeping in mind. So even though it's kind of like, I don't think anybody when they made these benchmarks thought that in, you know, 2020, like we'd be like, you know, pushing the level of human performance. There's still quite a long ways to go before this is just like at human level. Okay. So on the note of giant models, I have to say something about GPT-2 and GPT-3, which have probably received kind of significantly more hype than any of these other models. And so if you follow the literature, you've probably seen them. And as we saw with the original GPT, they're using decoder transformer blocks. And so that means that like one thing that GPT like works really well for, and kind of what it's marketed for, is as text generation. And so you give it a prompt and it will like continue with it. And so I showed some examples of this earlier in the class where you prompted it with something and it will produce more text. And they have like online demos of this. And so again, this is something where like, you know, the commercial objective is that this is going to power your customer service, right? You're going to be able to create kind of a chat bot with this, and it's going to respond like a human would. So unlike the other models that we've been discussing, it is not an open sourced model. Ironically enough, despite the fact that it's produced by OpenAI, for reasons you'll see, they needed to have a partnership with Microsoft. And I think like, you know, Microsoft aims to develop this as a proprietary product. And so GPT-2 is very large. Maybe it doesn't seem so large since I just showed you T5, but still at the time, okay, 1.8 billion parameters for GPT-2 extra large. And it does that by stacking 48 decoder transformer blocks. Well, GPT-3 just blows that out of the water because it's 96 layers deep. It stacks, its context window is 2048 versus the 512 for BERT, and it has 175 billion parameters. Like if you can even kind of like wrap your mind around that number. Which kind of goes back to what I said about it being like proprietary. So obviously you're never going to run this on your kind of like personal computer. Like this is going to go on to Azure and like power some kind of Microsoft product. But because it's not like open source, you're probably not going to see a GPT-3 Lite unless they decide to open source their training code. Because I mean, in general, it's understood what they did, but the details of it are not sort of fully out there since they haven't released the training code. But yeah, this thing is just, you know, like you probably thought a few slides ago that T5 was huge, but GPT-3 just, you know, clearly blows that out of the water, and you understand why OpenAI partnered with Microsoft, because the only way you're ever going to get enough compute to, you know, $4.6 million of compute, I think, to train this thing is to like, you know, be at Microsoft or Google. And it was also trained for downstream tasks like summarization. So I just thought this was kind of interesting. They took the Wikipedia summaries and the articles and used that to make it, you know, perform well on kind of that sort of task. And like part of the claim behind it too, there's been a huge amount of hype because like OpenAI, you know, claims that like, oh, we train this on so much data. They said with GPT-2, it's too dangerous to release. It's like so human-like that somebody could do something nefarious with this. And then people gave them a lot of slack for that, because probably the real reason they didn't release the code is because Microsoft, that was their agreement with Microsoft. But yeah, there's been like a huge amount of hype because the idea is that if you just train it on so much data, like it can essentially perform like a human because it's just been exposed to like everything, but actually it still doesn't perform like a human. And like anytime that there's hype, you know, people will make ridiculous claims on both sides, you know. So on one side, they say this is going to like replace everybody's job and like AI taking over everything is here. And then on the other side, like people will say, well, it's some kind of like psychopathic, like racist, you know, language model, which you can kind of cherry pick examples. But again, kind of the bottom line is like, it does pretty impressive, like without further fine tuning, but still not good enough that you would like actually probably put it in front of your customers, or that it would do like what you guys want to do for your projects, you know, without any kind of fine tuning, probably. So it's promising, it's huge, but it's not like a human yet. Okay. Everything we've seen so far, it allows you to look at relatively short sequences. And so BERT limits the length of the input sequence to 512 tokens, which they're like subword tokens, which are like largely words, but if they have certain like prefixes or suffixes, like those will be their own token. We just saw that GPT-3 is this massive thing that cost, you know, almost $5 million to train, and it allows a sequence width of, I think, 2048 tokens. In BERT, like there's no way to attend across these segments. And the reason that segment has to be limited is that computing attention is, the cost of that increases exponentially. It's order n squared based on the size of the sequence. So this is kind of a figure showing your standard attention compute. And you know, here this has been represented, there's these like separate batches and they can't attend to each other. So you get to 512 tokens, and then the next batch of text is fed in as the next batch. Or if you're evaluating, you can't have those long-term dependencies. And so that's potentially a problem. Maybe you care about some text where you need to attend to more than kind of that surrounding window of text that you can get with 512 tokens. And so we're going to talk about a few models that try to address this. So the first one is called Transformer XL. it introduces two features to overcome this shortcoming. And so first of all, there is the recurrence mechanism. And to integrate long-term dependencies, each hidden layer receives two inputs. It receives the output of the previous hidden layer of that segment, which is just the same as BERT. You're just feeding these hidden states like up the transformer stack, but it also receives the output of the previous hidden layer from the previous sequence segment. And that allows it to create these long-term dependencies potentially, where the gray out arrows, if you guys can see those, you know, it's coming from directly below, but then it's also getting these green arrows, which are allowing it to attend to the previous hidden state from the previous batch of 512 tokens that was fed into the model. And then these two inputs are concatenated and used to calculate the key and value matrices of the current head for the current layer for the current segment. And so this allows a given segment of text that's being processed to pay attention to that kind of hidden state from the previous layer. And then that's creating more of these kind of longer term dependencies. Another problem is, well, how do you do positional encoding? Because remember from the transformer block, the positional encoding depends on the position in that batch sequence. So if you're position 1, it would be the same. And that would be a problem with this model, because the positional encoding would be the same for the input that you're getting from your own kind of segment of text and from the previous segment of text. And that previous segment of text is different text. It's going to be of probably less importance in terms of attending to it because it's further away. And so the paper presents a new positional encoding that is part of, and essentially the difference is, remember with the transformer, you add the positional encoding, and with BERT and other things that just took the transformer, you add that positional encoding to the input. Whereas in Transformer XL, you're going to compute it at each layer, and it's going to be based on things like relative distance. It's actually kind of complicated. It involves several learned vectors. I'm not going to go into the details, but I just wanted to point out that you're going to have a different positional encoding that tells you the order of those tokens if you're attending to information from multiple batches. So Transformer XL was used in a model that kind of came to dominate it called XLNet. So it uses Transformer XL, but it combines that with a new training objective. And so BERT and ELMO improved on the state of the art by incorporating context, bidirectional context. And so XLNet takes this further by predicting each word in a sequence using any combination of other words in that sequence. And so this presents it with difficult and at times ambiguous contexts from which to infer whether or not a word is in a sentence. And essentially the intuition is that it allows the model to squeeze more information from the training data. So let me explain how this works. So if we have an autoregressive model like ELMO or like the OpenAI GPT, it looks at all contexts earlier in the sequence, right? It can look at all tokens from earlier in the sequence. Or if you like ELMO that was bidirectional, it ran the model forwards and backwards. The backwards pass could look at all tokens later in the sentence. What XLNet does is, like, suppose that you have a sentence with 4 tokens. You can consider all of the 4 factorial permutations, and then the XLNet model is autoregressive over the permutations. And it samples from all possible permutations. So let me give an example so that hopefully this will make sense. So consider that we take it's a forward sentence and we have a permutation that's 3, 2, 4, 1. When calculating the probability of the first element, which is token 3, the model has no context because remember, it's autoregressive. It can only look at previous things in the sequence. So there's an attention mask of 0, 0, 0, 0. It can't attend to anywhere else in the sequence. Now we get to the second element, and it can attend to things that come before it in this permutation. So it can attend to what is the third word in the original sentence. And so the mask is 0010. Following that logic, we get to the third element. And the third element can look at, in this permutation, can look at the positions 3 and 2 in the original sequence. So the mask is 0110. And then by the fourth element, it can look at 2, 3, and 4. So the mask is 0111. You put all those together in a matrix, and that's your attention matrix. So you remember, like with the decoder blocks, the attention matrix for an autoregressive model is just like below the diagonal of the matrix. Whereas with this permutation approach, you're kind of paying attention to all different portions of the sentence, just depending on what permutation you've drawn. And you do that kind of many, many times. And so it's a kind of a cool way to think about what context you're paying attention to. So it's like a masked, like attention model, but you're doing it in a more sort of sophisticated way that should squeeze more out of the data than if you were just doing like a normal kind of autoregressive model, like the decoder blocks in the transformer. So a disadvantage of this is that it takes a long time to train. It takes about 4 to 5 times kind of longer than BERT. And so this is the performance. And so it does better than BERT. It still seems that ROBERTa is maybe a little bit better depending on the benchmark, but they're kind of in a general kind of neighborhood of each other, doing a bit better than BERT. So yeah, that's kind of this table kind of sums up 4 of these models that we've seen so far. So ROBERTa and XLNet are going to beat BERT, but distilled BERT is going to be a little bit worse, but it's going to be a lot smaller. Okay, so I think we're going to have to wrap up the last 2 models next class, which are about what to do when you have long text. When 512 tokens just kind of isn't enough. And so that will kind of fit nicely into next lecture, but I'll just say quickly, and I'll come back to this next lecture. So what do I use? I think that kind of the bottom line is it depends a bit on your task, and we'll kind of, next class, we'll talk about the long text models just briefly, kind of we'll have a brief recap of what we saw today, and then I'll share some thoughts on which one of these you guys should actually choose if you're looking kind of for a model to use for your projects. All right, thank you.